Hi everyone, I'm Sam and I'm presenting on magnetic neuromorphic computing devices. So to quickly go over the summary, I'll go through motivation for spintronics and hardware neural networks first, and then I'll go into some background about neural networks. And then after that, I'll go over devices, which I split into categories based on mechanism. And then I'll wrap up with a discussion of challenges of the system level integration for conclusion. So as the size scaling of CMOS gets more and more difficult, different methods of speeding up computation are necessary. One of the ways to tackle this is by reducing the memory wall, or the separation of computing elements and memory elements. Neuromorphic computing alleviates this problem where memory and compute are distributed, allowing parallel operations, computer memory, and efficient implementation of classification, interpolation, and signal processing. And spintronics and magnetics are particularly well suited to implement this paradigm because they're non-volatile, they have low energy usage, they're high endurance, and also they're radiation hard. This last point allows advanced processing to be done on platform in extreme energy limited environments like space. So we'll start with what an artificial neural network is. So an artificial neural network, or an ANN, can be explained as nodes organized in layers that are connected to each other. The connections to each other can be abstracted as a matrix multiplication, shown in the equations to the right. The most typical way to train these types of networks is through supervised learning, where you introduce an image to the input neurons, in this case a handwritten digit in the bottom right. You can compare the output to the correct output, and then the network uses this error to adjust the weight matrix through stochastic gradient descent, which is also called backpropagation. As you can see from the network on the bottom, this is implemented in hardware using two artificial elements, neurons and synapses. So to build a neural net, your synapse must display memory abilities. So it must be able to save whatever state it's in. It also needs to be able to implement multiple weights, which is also called long-term plasticity, or LTP. And this can be done in a few different ways for spintronics devices. But lastly, it's also desirable for the states to be linearly distributed across the device and have symmetric update response to positive and negative impulses to be effective for backprop. Neurons, on the other hand, at minimum must display a summing behavior where it integrates incoming signals, and a thresholding behavior where it sends out an impulse when it has integrated enough. And this is known as integrate and fire. So you can see from in the graph to the bottom right, you can see that there's a relaxation behavior when the neuron is not integrating. It's called leaking. And this can eliminate a lot of training noise. And it's called a leaky integrate and fire, LIF neuron. So this leads into spiking neural networks. So LIF neurons are particularly effective in SNN implementation. SNNs are basically ANNs with time dependence, where impulses are not constant and instead they're spikes. Due to energy efficiency compared to ANNs, this is the target of a lot of neuromorphic devices. The main requirement for these networks is that synapses display spike timing dependent plasticity, or STDP behavior, where the synaptic change depends on the timing difference between a presynaptic and postsynaptic pulse. And this is a form of unsupervised learning. From the graph, you can see that if the pre comes before the post, there is a positive change in conductance, and if the post comes before the pre, there's a negative change, and there's some exponential behavior with regard to the timing. So diving into the devices, the first mechanism that can be exploited is stochastic switching, which was discussed by Professor Khalili. The devices are MTJs with a low energy barrier that can probabilistically switch from thermal energy. In spiking neural networks, information is encoded in biased Poisson distributed spikes, which yields the best results, which is a detail that I won't get into. And in Sengupta et al., they go one step further and show that the leaky integrated fire behavior of a stochastic MTJ is in the bottom figure there. This noisy switching speeds up the training of the network, and so from the graph in the top right, you can see that it actually trains quite quickly. So the error starts minimizing at, after about 10 training epochs. And you can also use these to implement synapses. It turns out 2 states is actually enough to implement a synapse, but since the devices switch stochastically after a lot of training epochs, the average result becomes closer to the ideal. However, the accuracy of 60-something% accuracy reached on MNIST dataset is far from acceptable. Srinivasan et al. Improves this by introducing an additional bit with a lower threshold that implements short-term plasticity or STP behavior. However, the bit resolution of the synapse remains a major hurdle. So software MNIST for 2 layers can achieve greater than 97%, but here you see that it only achieves around 72%. And so moving on to oscillation-driven devices. Oscillation-driven devices are intuitively useful for frequency-dependent tasks like voice recognition. So this can be implemented in MTJ using a spin-torque nano oscillator, or STNO, where a constant current will induce precession of the free layer. So the ability to encode and multiplex information and frequency can actually lead to a single device that's able to implement an entire neural network. Torrejon et al. Performed classification of spoken digits using process data using a single spin-torque nano oscillator and reached near ideal software classification. And you can see that in the graph on the top right versus around 10% for the unprocessed data, which is about equivalent to a random guess. Another approach to multiplexing information and structure that is not an MTJ is through a spin-Hall nano oscillator, or SHNO, shown in the bottom right, to multiplex 20 frequency responses using a 4x4 array. They didn't apply this on any neuromorphic task, but in general, the problem with these is they're not as mature as MTJ technology and have difficulties in flexible control and readout. And so we're going pretty fast, but I'm going to go into domain wall-based devices. So as we learned in class, domain walls are spin textures that separate 2 domains of uniform magnetization, and they can easily represent the neuron using the position of the domain wall as well as the weight of a synapse. Spintronic domain wall synapses are well suited for implementation of backprop, since they're shown in recently accepted work to apply physics letters that their states are highly linear symmetric. They have extremely fast updates for online learning, and with moderate resolution even at scaled sizes. So in this case, there's 32 weights available. And the bottom right shows that they have close to software performance for the more difficult fashion MNIST dataset. And they were also shown in Akinol et al. That they have STDP response. So this can be adapted to SNNs as well. And this is for a Hallbar 4-terminal device. So you can see experimentally that they show that they have linear symmetric weights with a large amount. So this is with a maximum of 70 weights shown. And for interest's sake, these are experimental results from Lequeux et al. And Chantwala et al. For multi-weight 2-terminal synapses. And then these can be considered memristors or resistors that remember how much current has passed through. So Professor Incorvia covered bio-inspired neuron behavior. So I just want to emphasize here that more complex behaviors like lateral ambition, edgy relaxed behavior, leaking behavior due to shape and crystalline anisotropy have been emulated in domain wall neurons. And then finally, the final mechanism is skyrmion-based skyrmions. And so skyrmions is a more novel spin texture, and since they're small and current controllable, naturally they're ideal to use for neuromorphic memories. An example is using a swarm of skyrmions to implement synapses. These are 2 different devices with similar structure of having a chamber that can sense resistance change based on how many skyrmions are inside. For a chamber with a lot of skyrmions, the trained accuracy for the MNIST dataset is very close to software due to many weights, linear and symmetric response. So here are the experimental results obtained by Song et al., including smoke images of the skyrmion swarm. So the top row is the potentiation of the synapse, and the bottom row is the depression. So this behavior can also implement neurons when a certain number of skyrmions has entered the chamber, reaching a threshold. So skyrmions can also implement a special type of neuron called resonating fire here. So as you can see, it's just sort of a breathing neuron, and using a voltage control magnetic anisotropy element underneath, you can induce frequency dependent band response. And so I know there's going to be another presentation on skyrmion reservoirs, but skyrmions can complex Skyrmion lattice can also implement this kind of really complex reservoir, which can implement an entire neural network. And so very quickly over some system level integration challenges. So
okay, we went over, it's at 10 minutes, so just try to wrap up in a minute.
Yep, yeah, this is the last slide. So in general for spintronics, there's a really small on-off ratio, which requires more complex readout circuitry. And device-to-device variability, which results in nonlinear and asymmetric weights, happens a lot. So this requires a large improvement in etch techniques, particularly true for magnetics. Some neural network techniques can alleviate this, but this is still necessary. And for circuit level integration, power transistors are required to drive the devices are quite large since the current required is quite large. Some types of devices that can represent entire networks in a single element can alleviate this problem. All right, any questions?
Thank you. Questions for Sam?
I have a quick question about artificial neural network. I think it is model that in computer science, and we can realize it now without the use of spintronics devices. So I would like to know what is the advantage if we apply spintronic device to like these kind of models?
So basically these can be applied sort of in hardware neural network accelerators. So in conjunction with traditional computing. Basically this allows a lot of tasks to be offloaded onto this piece of hardware instead of doing complex calculations between memory and computation and memory and computing elements. In using spintronics, spintronics are fast compared to a lot of other memory technologies. And so in this case, spintronics is well suited for stuff like online learning, where you can learn based on inputs on the fly.